So today we'd like to welcome Dr. Heather Lynch. She's at the Institute for Advanced Computational Sciences. She's the endowed chair for ecology and evolution at Stony Brook University. Following a Bachelor's of Arts in Physics from Princeton University and a Master's of Arts in Physics from Harvard University, she received her PhD in orgasm and evolutionary biology. That's a hard word, Heather, from Harvard University in 2006. Dr. Lynch's research sits at the intersection of statistical ecology, geography, applied math, and computer science. Her research is focused on all aspects of conservation ecology in the Antarctic, with a particular focus on the integration of satellite imagery and traditional field work to map the distribution and abundance of Antarctic wildlife and to predict how populations will be impacted by climate change, fishing, and tourism. So we're very glad to have Dr. Lynch as one of our speakers, as her interest area and presentation addresses one of the U.S. CLIVAR POS panel priorities, and that's the marine ecosystem dynamics for climate at the coast. Further, this presentation is one of several oriented around the theme of quantitative and foraging ecology in preparation for the joint US CLIVAR and OCB ecological forecasting workshop that now will take place in April of 2022. So to that effect, Dr. Lynch will be presenting the Antarctic marine predator populations are difficult to forecast. Can climate models help? And thank you so much again for agreeing to present, and we look forward to your presentation.
Excellent. Well, thank you so much for the introduction. So I'll just jump right in. Penguin dynamics are really difficult to forecast. So I'd love to hear what you guys might have to think. The work that I'll be talking about today involves a large number of people, some of whom are listed here. But in particular, I did want to highlight the efforts of Christian Castaldo, who's a co-PI in our most current award, and sort of the computational talent behind the mapped application I'll talk about in a second, as well as Bilgejan Zen, who's a postdoc. So I'm not going to talk a lot about the Antarctic ecosystem, although I'd be happy to later. But the key thing is, as many of you are no doubt aware, that the Southern Ocean ecosystem is really run by Antarctic krill. Antarctic krill are the sort of keystone species of the Southern Ocean food web. And one of the challenges of studying Antarctic anything really is that Antarctic krill live in these giant swarms that are very difficult to measure, and they're very patchy. And so a lot of Antarctic ecology is really looking at Antarctic predators as a window into the Southern Ocean ecosystem that's difficult to observe directly. So a lot of my work focuses on the development of this tool that we call the mapping application for penguin populations and projected dynamics. And this was a NASA-funded project, maybe funded about 8 years ago now, that was designed to unite satellite imagery and field counts. We can get penguin population counts both from direct measurements, but also from drones and satellites, and to connect that on the far right-hand side with decision support tools that would be valuable for policymakers. In the middle are the models that I'm going to be talking about today, which integrate these streams of sort of disparate data coming in from various sources and try and repackage it into policy relevant forecasts that could be used for policymakers in the Antarctic. So as some of you might already be aware, the Southern Ocean is divided into different management zones for the purposes of managing Antarctic fisheries, principally Antarctic krill fisheries. And spatial management of these Southern Ocean resources requires real-time tracking of Antarctic predators, again, because the predators are telling us something about the distribution and abundance of krill. And the species that I study are these 4 penguin species here: the emperor penguin, the Adelie penguin, the gentoo, and the chinstrap. Unfortunately, the data that we have on these penguins and other seabirds is extremely patchy. And so that really drives a lot of our modeling decisions. So I talk about 3 different regions in my talk today. The Antarctic Peninsula, which is much more temperate, much more sub-Antarctic in its climate, the Ross Sea, and then everything else, which we refer to generally as Eastern Antarctica. So just to give you a sense of the patchiness, this is a bit of a schematic, but you can imagine having all of the breeding colonies, and today I'm going to be talking mostly about the Adelie penguin. We can think about the breeding colonies on the rows of this matrix, and the columns represent years, and an X indicates that we have some information about the abundance of that penguin population in that year. And what we're typically doing in ecology is that we are taking one location, say location 10 in my little diagram here, and we would create a long-term monitoring study that would allow us to track the abundance of a population through time and hope that the dynamics at that location were representative of the trends at other locations. But from a management perspective, we're often wanting to sort of cut across this matrix in the other direction, which is that we want to know, okay, in 1984, how many penguins were in this management area? And so when we're looking at the data in that direction, we can't just focus on the sites where we have very continuous time series. We actually have to deal with the sites where we have very little data as well. So I won't get into the details of our model so that we can talk about them later. Just as an aside, reproducible research has been a huge effort of my lab over the last decade. Our markdown document describing these models, if you were to print it out, as I once did accidentally, are over 600 pages long, and they allow anybody to download the data and the code and rerun it from scratch. But broadly speaking, we differentiate between what we call a process model, which is actually describing the evolution of penguin abundance over time and its relationship to the environment, and an observation model, which reflects the fact that all the data that we have come in with varying levels of precision. And so we have to separate out that observation model from the actual true dynamics. The goal at the end of the day is to use these hierarchical Bayesian models to fill in this matrix. So we might start out with a matrix that's very patchy of our observations, but we want to move to a completed matrix of true abundance where we've used our model to infer the abundance in sites and years where we didn't have direct observations. Now, the key question here is, what are the environmental drivers of population change? If the population goes up, we want to know why it went up, and if it's going down, we want to know why it goes down. So all of this work is really trying to understand which environmental covariates are important for penguin population dynamics. And our first effort at doing this was restricted to observed variables, particularly sea ice concentration, because it can be measured from passive microwave, and we have direct observations for what's going on in the environment. And what we found was that penguin growth rates, Adelie penguin growth rates, are high when you have lots of sea ice in the winter and very little sea ice in the summer. So it turns out that most colonies sort of satisfy the condition that they have low sea ice in the summer, but where colonies are declining, it's because they lack sufficient sea ice in the winter. And if you look on the right-hand side here, I'm just illustrating sort of the coefficient, the parameter estimates from this model. What you see is that both winter sea ice and summer sea ice are statistically significant in our models. But if we rank the importance of these covariates in terms of their ability to explain fluctuations in penguin abundance, what really dominates here is what we call a year effect. So this is just stochastic year-to-year fluctuations in abundance, where all the penguin populations in Antarctica are having a good year, or they're all having a bad year. So it's not local sea ice conditions, but really this unexplained stochastic variation that's sort of causing all boats to rise or sink in tandem. Now notice that we only fit a linear relationship here, and I'll come back to that a little bit later. So if we just sort of zoom out and we say, well, what do our models say about what penguin populations are doing? Penguin populations are growing. Adelie penguin populations are growing. But that growth is highly heterogeneous. So what we have are very rapid growth rates in eastern Antarctica, but on the Antarctic Peninsula and the subantarctic islands, where climate change is having some of its most dramatic effects, we see populations that are either declining or at best stable. So overall they're growing, but that sort of belies this sort of haves and have-nots pictures across Antarctica. The data that we have are extremely noisy at individual sites, but as we aggregate over larger and larger spatial scales, what we get is this robust picture that emerges, and that speaks to the benefit of our strategy, which is to fill in all the gaps, as it were, to infer all of those unmeasured data, all the data that we're missing. We're making estimates about what the abundance would have been. So here I'm just showing you what the model looks like in sites where we have lots of data and sites where we have very little data. And we kind of call these models connect the dots models. Essentially, in some sense, they're pretty over parameterized in that they can capture all of the flexibility in the data if you have it. When you don't have it on the right-hand side, you can see that the uncertainty, these credible intervals, explodes between data points. So our uncertainty, as it should, grows when we don't have any data. But what the model's trying to do is essentially to say, well, I'm going to use these sites where I have a lot of data to learn that relationship between penguin abundance and the environment. And I'm going to sort of impose that to make some best guess about what's going on when we don't have any data. Coming back to these year effects that I mentioned earlier, these kind of good years and bad years, I just want to highlight 2001 as an example here. 2001 was a year in which many of the penguin colonies in Antarctica declined in abundance. And you can see that for a small population like Litchfield Island, it actually was immediately followed by the extirpation of that population. So this population was small. It was hit by this sort of extreme event, and then it blinks out shortly thereafter, whereas this Cape Crozier population is very large, and while it suffers the same effects of whatever happened in 2001, it bounces back and recovers. So these extreme events are very important, and in some cases can tip a population into extirpation. And yet we really don't know what drives them. So we spent a lot of time trying to look at what environmental variables relate to these extreme years for penguin abundance. And we looked at things like southern annular mode and southern oscillation index, ice advance and retreat and duration, and pretty much any index or climate variable that we can observe, we looked at, but nothing really popped up as being like, oh, that's why 2001 was a bad year. That's why 2006 was a bad year, and so forth. The good news is that our observation error, while it's considerable, is actually not hindering our inference at this point. So here I'm just showing you, well, how much of our data would be in considered plus or minus 5% measurement error, how much plus or minus 10%, how much plus or minus 25%. Well, it turns out that our unexplained process error, just the unexplained stochasticity in the dynamics, is equivalent to plus or minus 50% observation error, and most of our counts are actually better than that. So even though our data are in some cases highly imprecise, that's not the reason that we're having trouble understanding the dynamics. The dynamics are just really noisy, and we don't know why. Now, this unexplained random variation in growth rates drives an enormous forecast uncertainty. So here I've sort of simulated an ensemble of trajectories over 25 years for a population that should have stable dynamics. And you can see that the forecasting cone sort of explodes quite rapidly. And here I'll just show this cartoon, which I think captures it well. And the caption says, as you can see, this model smoothly fits the weight. No, don't extend it. Ah! And that's kind of what our model's doing, right? So it does a really good job in the past, but it really does a terrible job in the future. So at the end of this project, or nearing the end, we had this sort of crisis of confidence in a way. And we said, look, maybe all of this knowledge we have about the Antarctic is not helping. What if we just crowdsource the model development? And so that's exactly what we did. We went back to NASA and asked for a supplement to our award to host a data science competition with driven data. We had $16,000 worth of prize money. We put all of the data out there on the internet, told people about the system. Can you make a good prediction? We in fact then had to scrape the internet of all of the data, the last 3 years worth of data that we withheld as a test set. You can see the prizes here. And in particular, we had a prediction bonus for 2017. So at this point, it was 2016. This is like the ultimate and out of sample prediction, because we're asking people to make a forecast for 2017. We would go down into the field, count how many penguins were at all these sites, and see who did the best job. So they were being tested on their ability to predict 2014, 2015, 2016, but also this like truly out of sample future date of 2017. What we had at the end, we got almost 600 unique models that were submitted in 60 days of competition. As a way of engaging citizen scientists, it was kind of a new approach for us, but it really got people excited about penguin dynamics, people that we had people from all over the world trying to build good predictive forecast models for abundance. These were the 5 winning modelers. And we went and wrote a paper with them on what we had learned from their short-term forecast approaches. They all took different approaches. So what we learned was that our model, the model that we'd developed as penguin biologists, was competitive with the best submitted models. It would have been in the top 5. It would not have been the best model. So we were in the right ballpark. But the environmental covariates did not improve short-term forecasting accuracy. None of the winning models used any of the environmental covariates that we had provided. These domain-agnostic time series forecasting approaches yielded good short-term predictions that were as good or better than the ones that were derived using more biologically driven models. So we know a lot about penguin dynamics, but all of that knowledge is not helping us with our short-term forecasts. This data science competition was a great way of getting other communities engaged with this ecological data set. But the forecast horizons remain stubbornly short. It's, in fact, I think the second best model was essentially a random walk. Like, it was assuming that your best guess about next year is whatever the abundance was this year. And this makes it difficult to link our model for dynamics to predictions for future range shifts under climate change, because the environmental variables are just not strongly predictive. So time went by, as time will do, and we continued to work on this, and more recently got a new grant from NASA to continue working on this. The 3 things that are new in this most current research is that we're incorporating an ecosystem model, essentially a food web model, that we didn't have before. And this was to try to address the very fair criticism of our prior attempt, which is that penguins don't eat phytoplankton. Now, if the only way that the food web is entering our models is through chlorophyll A, because that's something we can observe, we are assuming in some sense that penguins eat phytoplankton, or at least that there's not such a big gap that chlorophyll A concentrations isn't at least somewhat indicative of biological activity, but it's a stretch. So we wanted to fix that. We wanted to explicitly separate out short-term and long-term fluctuations in terms of they may have different drivers. And finally, we wanted to use climate models as opposed to environmental observations to incorporate environmental conditions that are not directly observable. So just to address the first issue here, I'm not going to talk about the food web model in detail, but this is crudely speaking what that model looks like, and it allows us now to actually start looking at, carbon pools in small microzooplankton as opposed to large. In terms of dividing long-term and short-term dynamics, I'll just say that today I'm just going to be talking about our efforts to, again, focus on these short-term annual fluctuations, which is how does the abundance in year T change between T and T+1, and what environmental variables might be responsible for that year-over-year change. Again, kind of coming back to this process model, the logic here, just to emphasize, is that if we can better model the environmental variables that are important, we can reduce the amount of process error, right? There's a certain amount of variation. We're trying to partition that variation and scoop as much variation out of the, I don't know class and put it into the environmental variables class, because it's that process error that's driving the explosion of our forecast sort of ensemble uncertainty. And again, the logic is that if we can explain the year-to-year fluctuations in penguin abundance, that we can better forecast future penguin abundance. And I just put a note here, that's not a tautology. Like, it's not obvious if that's true. If A, then B. I don't know if that's actually the case, but that's sort of the logic of our current approach here. So when we move from climate observations to climate models, we're left with this paradox of choice, right? To now, instead of having maybe half a dozen or a dozen things that we can observe, sea ice, chlorophyll, sea surface temperature, now we have hundreds of variables that are coming out of these climate models, and it's really hard to know which ones to consider. So we tried an informal expert elicitation process. We tried random forests. The other question that we have is, sort of at what spatial scale? So we've developed these, what we call sort of as the penguins swim buffer zones that incorporate obstacles and land masses to try and figure out, well, what part of the ocean is important for a penguin colony at different radii. And the challenge is that as biologists, we want these radii to be really small because we want it to reflect the ocean that a penguin might actually be experiencing as it's coming to and from a colony. But the climate modelers feel very uncomfortable going to these very small scales, particularly when you get down to a single pixel, because from their perspective, they think that there might be artifacts at individual pixels that are sort of averaged out when you go to 500 kilometers or 1,000 kilometers. So between sort of the biologists on the project and the climate modelers on the project, there's a bit of a tug of war between wanting information at very local scales and the climate modelers feeling that they don't maybe trust the models at those fine scales. And finally, we have to think about temporal scale. And I'll just say here, we've binned up into quarters. So, winter, spring, summer, fall, essentially, rather than look at daily or even monthly climate model outputs. These are the variables that we examined using random forests. There's a whole ton of sea ice variables, a bunch of food web variables. I'll just say that we're still struggling with what some of these variables mean for penguins. So divergence rate and volume tendency dynamics, like from a physical perspective, we can get a definition, but what that means for a penguin is still a matter of debate. So I'll just say that, these are these variable importance plots just showing which variables the random forest models would say are important. The main take-home message is that on the Antarctic Peninsula, we do see some evidence that the food web variables are important, in particular the carbon pool among the small microzooplankton at 250 kilometers radius. So there is a food web variable that shows up as being important, but overall we have pathetically low variance explained. Whereas in the Ross Sea and Eastern Antarctica, the sea ice variables are very much dominating here, but we have higher explained variance. Nevertheless, the amount of explained variance is pretty low overall, considering that we've thrown every climate model variable in here that we think could possibly have been important. What we ended up putting in the model are these variables that you see here, mostly relating to things like divergence, which we think relates to leads and cracks and other openings that would allow penguins to get in and out of the water while they're foraging. And there was some good news. So there are some biologically reasonable interactions. So here, if we look at ridge ice area and divergence rate, for example, there appears to be a zone where population growth is negative. There's a zone where population growth is positive. And these are variables that we at least can imagine are related to what penguins are doing in the ocean. So that's good. And we see this hypothesized interior maximum. So here's from the proposal, actually, you can see just schematically that we imagined that there was this sort of Goldilocks zone in the middle where, an intermediate sea ice area, penguins might be really happy. And if it's too low and it's too high, they're not happy. And that's in fact exactly what we see. So we do see sort of an internal maximum here showing that Adelie penguins want sort of intermediate levels of sea ice concentration. So these non-linear responses are what we probably would have expected. Unfortunately, though, the scale of variation in the population growth rates is much larger that can be explained by environmental drivers. So those dashed lines in the figures are showing you how much variation can be explained by the environment. And then those jagged lines are showing you population growth rate from all of the different populations. We get extreme fluctuations in abundance that have no obvious link in the climate model variables that we're looking at. And still the explained variance is too small to be useful for forecasting. So we're, so maybe the climate models provide some insight that we didn't have before, particularly when it comes to sort of sea ice physics and things like divergence and strain rates. But we're not where we want to be in terms of being able to make better forecasts. So finally, just in terms of next steps, one thing we're looking at is asking, can we even just predict the sign of penguin abundance change? Like, are penguins going up next year or are they going down next year? It doesn't look like that we can do that any better, but that's something we're looking at. Maybe we need to throw all these variables into some sort of principal components analysis because they are so highly correlated among them. Random forest method that we're using is well adapted to highly correlated variables, but maybe PCA would get us somewhere. It does assume that these relationships would be maintained under climate change, which isn't obvious. We're looking at maybe doing a weighted average of forecasts over different timescales. So maybe using a year over year sort of short-term forecast for 1, 2, 3 years out, and then gradually shifting to a forecast that's designed for much longer timescales. So I'd be kind of curious in any suggestions that you might have on that. And finally, as will be obvious to you, but wasn't obvious to us getting into this project initially as biologists, is that when we think about what variables will help us better forecast penguins, we have to find variables that are both important for penguins, but that are themselves forecastable. So if covariate X is intimately related to penguin population dynamics, but covariate X is very poorly, or with poor precision, whatever, very poorly forecasted, it doesn't actually make our penguin forecasts any better. So that's something that we're exploring right now. And lastly, I'll just close by saying that some of you may be already aware of the ecological forecasting initiative, but it sounds like there's a real interest within this group in short-term ecological forecasting, and that's something that this group has been also very interested in. And in 2019, Mike Dietz from BU and I organized the Ecosystem Forecasting Conference, where we brought in a whole bunch of people to talk about sort of the technology of short-term forecasting and also its connection to policymakers. So I would definitely encourage you guys to go to EcoForecast.org if you're not already kind of on that mailing list or involved in that Slack channel, because I think that community of people, more on the terrestrial realm than the marine realm, but they're interested in all the same questions that I think you guys are as well. So with that, I'll just take any questions you might have. So thanks so much.
Thanks, Heather. I think we'll take the next 5 minutes for questions. Anyone on the panel? I think this is a pretty small group, so if you have a question, feel free to just unmute yourself or type it in the chat box.
Well, Heather, I have sort of 2 questions for you. That was a fantastic presentation, by the way, super exciting. It just made me think of like lots of questions. So the first one is with regards to sort of the penguin populations. How are you actually knowing where exactly they are? Is it more so by tags associated with them, or perhaps like satellite? Because I know I've seen some of your papers with regards to Landsat and looking at the penguin poop. So I was sort of curious how that was sort of done.
Oh yeah, great question. So I should have said that right at the beginning. So we're just looking at the abundance of penguins at their nesting colonies. So we now know where all modulo 1 or 2, maybe we haven't found yet, but where all Antarctic penguin colonies are. And so we now know, okay, here are there's just shy of 1,000 Antarctic penguin colonies, and we can track the abundance at those locations through time. So at least it's a static list of locations that we're tracking, and we're not at this point including non-breeding individuals that might be out in the ocean. So just the breeding population at this point.
Gotcha. And then I had one other question. It's more like a sort of larger thinking, because you mentioned, which is great to know, that the existing environmental observations aren't necessarily the problem. It seems that perhaps you just don't necessarily have the observations necessary. So it seems you used a model, which completely makes sense. But if there was a sort of observable that we could get from spacecraft, for sort of better teasing that out, what would it be? Would it actually be on sort of the more on the krill type level, or nutrients themselves? What would you say that would be?
I know exactly what I would be on my wish list, which is that we don't have good measurements of precipitation, particularly rain. And so we know that rain is really important for penguins, because what we have is this shift, particularly on the Antarctic Peninsula, between snow and rain. And so I've spent quite a bit of time. First of all, there are very few direct measurements of rain in the Antarctic, usually because it arrives sideways, and so it just sort of befuddles, rain gauges. I've also spent some time sort of talking with the NASA precipitation measurement team, and they have felt very uncomfortable with their measurements in the Antarctic, because there are so few measurements sort of to ground their model, but also because the models it's sometimes difficult to distinguish between rain and snow. I have looked at using MERA too and some of the reanalysis products to look at precipitation. Where we do have observations of rain, it does a surprisingly good job. So it's funny talking to the precipitation people, and they would say, it's not going to work in Antarctica. It's not going to be any good. But the R-squared relationship, the correlation between these reanalysis products and measurements of like, did it rain today? Like how many days this month did it rain? Those R-squared values are actually pretty good, like, 0.7 or 0.8. But not being able to measure rain has been one of our biggest unknowns. And so if there was a way to improve that, it would make a big difference for our models.
Oh, fantastic. Thank you.
Heather, I have a quick question for you.
Yes.
Thank you very much. I thought that was a very, very interesting talk. So how long do penguins live?
So their average life, because there's so much juvenile mortality, is maybe just 2 or 3 years, but they can live, if they sort of survive those early years, they'll live to be maybe 12, 14, 16.
Get it. So, all right, so now a more serious question. So my understanding from your talk is that there is this mystery interannual viability that you cannot explain, right?
Yeah.
But yet, you do some advanced statistical analysis and modeling. And so as you were talking about the uncertainty and observations and how this, those very sparse, uncertain observations cannot really constrain reanalysis products, as well as, climate indices, that are calculated from these products, et cetera, et cetera. But so that error you have in the year-to-year abundance is still yet larger than the uncertainty on the prediction?
Yep, absolutely. So our it is much, much larger than the uncertainty that we have from our observations, surprisingly. So when we went into it, because we're very self-conscious about our, plus or minus 15% or something, seems like we have these huge error bars, but then we look at the genuine fluctuation in the abundance from one year to the next, and it's much larger than that. So we don't think at this point we're limited by our own ability to count penguins. It's that they are fluctuating for reasons that remain a mystery. I will just say, this came up even just yesterday, talking with my postdoc. There is strong residual autocorrelation in those fluctuations. And because penguins are not moving among sites, they're highly site faithful. So there's no actual movement among these populations. The fact that these populations are fluctuating in an autocorrelated way suggests that there's something in the environment that's driving it. There's sort of, because the environmental variables are themselves spatially autocorrelated, but it's just interesting that something in the environment is driving their behavior, and it's nothing that comes out of these climate models or the food web models or the sea ice models. It's almost, it's kind of hard to even think of what would be left. But at least this remaining variation is spatially autocorrelated, and it gives us a somewhere to start looking, I guess.
Okay, so, and just to clarify, you were talking about, correlation with climate modes. And so you've taken into account uncertainty on how much we know about these modes, right? When it could, if you look at MERA2, or if you look at, ECMWF, calculation, you're actually going to find different climate modes, but you've taken that into account. Yeah.
Yep. So we looked at it every, and I should say this was very much work that Laura Landrum at NCAR had been key in this, because we wouldn't even know sort of where to start. But that was the first thing that came to mind, is that it looked like something that some sort of climate mode might explain, and yet nothing that we threw at it really made a difference. So that surprised us. Particularly 2001 is interesting, because 2001 was associated with a whole host of weird reports that came in having to do with areas of complete breeding failure, like Weddell seals not showing up. Like, it wasn't just penguins, it was across multiple species. It was from one end of the Antarctic to the other. And it was interesting, if you look at all the papers, a whole bunch of different groups published papers on 2001, but they all had their own boutique explanations. So over here, they're like, oh, it's because of a massive iceberg. And over here, they're like, oh, because it rained too much. And over here, they're like, oh, it's because of some other reason. But in fact, I think something happened in 2001 that was affecting all of these different systems. So it's just kind of interesting. It wasn't even just a single species. It wasn't even a single taxa. It was both marine mammals and seabirds seemed to be impacted.
Thank you very much.
I think we'll take one final question from Isabella.
Excuse me. Thanks for a great talk. That was fascinating. You alluded to the issues that climate models have sort of modeling the coastal Antarctic region. Have you done any work with regional ocean models in that area? I know there are a few.
Yeah, no, it's a great question. Actually, just right now, I'm working on a proposal with a potential postdoc who works on these regional ocean models to think about. I don't have any experience with them, but she does, and we're thinking to put our heads together to look at whether these ocean models that had been developed very specifically, for example, for the Palmer Canyon area on the Western Antarctic Peninsula, would relate to any of the things that we can measure from penguins. I will say now that we can see, I didn't talk about this part of our research, but we can see penguin guano from satellites. We can now estimate the abundance of all the penguin colonies in Antarctica annually, and we can do that with Landsat, so we can go back to 1979, even earlier, because we're looking at the earlier Landsat MS data. But not only that, we can measure penguin diet. So because the color of their guano is so indicative of their diet, we can actually start to get not just abundance, but diet. And that's where I think that we're likely to see some real benefit of looking at these regional ocean models, because there might be something in the circulation patterns that would, because krill are not very strong swimmers, if they're sort of being, advected out of an area, we might see that in the penguin diet. It might not, because they're long-lived birds, and we might not see it in their abundance. They're kind of, but we might see it in their diet, that they're switching to other prey because they have to.
That's really cool. Thank you.
All right, I think we'll end the webinar here. So thank you so much, Heather, for your presentation. And thank you for the PAWS members who are on the line. So our next PAWS webinar is July 1st. That will feature Elliot Hazen using Earth system observations for climate-ready ocean management. So again, thank you so much, Heather, for your presentation.
Thank you all. I really appreciated it.